Hi everyone, this is Mrs. Richart. Welcome to our introduction of rational functions. So what is a rational function? A rational function is a function whose rule can be written as a ratio of two polynomials. The root word of rational is ratio, and a ratio is like a fraction. So a rational function looks something like this: a polynomial divided by a polynomial. For a parent function of the rational function, we've looked at lots of different parent functions, such as absolute value, linear, quadratic, cubic, quartic. Now we're going to take a look at the parent function of a rational function. The parent function is 1 over x. To look at the parent table, we're going to plug in some negative numbers, 0, and positive numbers. The negative 2, if you plug it in, you have 1 over negative 2, which is negative 1/2. We can plot that on the graph. If you plug in a negative 1, 1 divided by negative 1 is negative 1. We can plot that on the graph. Plugging in 0, I get 1 divided by 0. 1 over 0 is undefined, so we just put a line through there. 1 divided by 1 is 1, plot our point, and 1 divided by 2 is 1/2, plot our point. A rational function has two parts because it's separated by 0, because 0 is not in our domain, since when we plug in 0, we don't get an output. So if I go ahead and sketch this rational function, notice it has two parts. It gets really close to both the x and y axis, but it doesn't cross, it doesn't touch it. If you look, it gets close to that y-axis. We call this a vertical asymptote, or x equals 0. The vertical asymptote is at x equals 0. That is the same as the y-axis. It gets super close, but it never crosses. Similarly, we have an x-axis as in horizontal asymptote, and the horizontal asymptote is y equals 0. It gets super, super close, but never touches. If we want to look at our domain we say is negative infinity to 0, union 0 to infinity. This means that our domain goes from negative infinity to 0. We take a break at 0 and we pick up our pencil and we start again, 0 to infinity. Because our rational function is in two different pieces, so is our domain. Similarly, we have our range, and the range is negative infinity to 0. We pick up our pencil, take a break at 0, 0 to infinity. Notice how the domain and range corresponds to the asymptotes. Now we're going to look at transformations. So we have done transformations of all different types of functions, absolute values and polynomials. The same rules apply. So you're going to be adding a slide to your transformation toolkit today, and you can use that, remember, on all quizzes and tests and assignments. So here's our transformation form. Y equals a over x minus h plus k. For rational functions, we're not going to do much with the b value or the horizontal stretch or compression. We're going to focus on reflection over the x-axis, vertical stretch or compression, shifting left and right, and shifting up or down. Notice that we have a vertical asymptote at x equals h and a horizontal asymptote at y equals k. For our transformations, here's some examples. So transformation, a reflection over the x-axis for a rational function looks like this, negative 1 over x. A vertical stretch, for example, is when the a value is bigger than 1, 3 over x. Vertical compression, the a value is between 0 and 1, so 1 over 3x. Shift left, inside is opposite, so it looks like it should be an x minus, but we know it should be x plus, 1 over x plus 3. Similarly, shift right is 1 over x minus 3. Shift up, we have 1 over x plus 3 on the outside, and shift down, we have 1 over x minus 3 on the outside. We're going to take a look at two examples that combine everything we've learned with transformations. So our first example is 1 over x plus 1 plus 3. So if we start with our parent table, we have negative 2, negative 1/2, negative 1, negative 1, 0, nothing, 1, 1, and 2, 1/2. So we want to go ahead and transform this parent function. Notice I have x plus 1. So we know what goes with x is opposite. Inside is opposite. So x plus 1 becomes x minus 1. We're going to go ahead and subtract 1 from every x value. Negative 2 minus 1 is negative 3. Negative 1 minus 1 is negative 2. 0 minus 1 is negative 1. 1 minus 1 is 0. And 2 minus 1 is 1. To figure out the rule on our y values, I have this plus 3 on the outside. So So I have y plus 3. If we add 3 to every y value, negative 1/2 plus 3 is 2.5, negative 1 plus 3 is 2, and we'll plot these points. I have nothing plus 3, so I don't have anything there. That's going to become my asymptote. 1 plus 3 is 4, and 1/2 plus 3 is 3.5, and we're plotting these points. Notice we have two sections again. If I graph these, I notice that I have a vertical asymptote at negative 1, and I can write that as x equals negative 1. I have a horizontal asymptote at 3. I can write that as a horizontal asymptote y equals 3. If you notice, from our asymptote, original intersection point of the asymptote at 0, 0, I move left 1 and up 3. Left 1 and up 3. And that's actually where our rational function moved. The domain, we have negative infinity to negative 1. We take a break at negative 1 and pick back up again from negative 1 to infinity. For the range, we have negative infinity to 3, pick back up again from 3 to infinity. So we have that break in there because it's not a continuous function. For our transformations, we have a shift left of 1 and a shift up of 3. And notice that's also what the purple and green arrows are showing. Shift left 1 and up 3. For our second example, we have f of x equals negative 4 over x. Our parent table of a rational function remains the same. We're going to transform this table of points in order to find our new transform function. If you notice, nothing is happening to the x. Nothing affects the x value. So we're going to simply copy down the x column of the parent function. I have a negative out in front that's going to affect my y value, and I have a 4 out in front that's going to affect my y value. So I have negative 4y as my transform rule for the y's. If I take negative 4 times every y value, I have negative 4 times negative 1/2 gives me 2, and I'll plot that point. Negative 1 times negative 4 is 4, plot that point. I have nothing, so I have to put a line there. Negative 4 times 1 is negative 4, and negative 4 times 1/2 is negative 2. So notice I have my rational function into two different sections. So if I go ahead and sketch those graphs, I have asymptotes, the vertical asymptote at x equals 0 and the horizontal asymptote at y equals 0. It hasn't changed from the original function, the parent function, because I haven't shifted left, right, up, or down. I've had other transformations affect this graph. So for our domain, it's the same as the parent function. Negative infinity to 0, pick up my pencil, 0 to infinity. For the range, negative infinity to 0, pick up my pencil, take a break, start back up again, 0 to infinity. And lastly, our transformations, we have a reflection because the negative and a vertical stretch because the a value 4 is bigger than 1. So we have come to the end of our lesson. The only assignment you have today is to add the slide for the rational functions to the transformation toolkit and ask your teacher if you have any questions, and be prepared for tomorrow's assignment. Have a great day.